equaling 0. Well, look, luckily for us, it's already a fraction, isn't it? So all I really have to do is figure out where what's 0. The top. 2x plus 1 equals 0. And that's just a little linear equation. Subtract 1, divide by 2. You get negative a half. Negative a half. All right. How about where it doesn't exist? You have to be worried about that denominator being 0, don't you? Will it ever be 0? No. How do we know? We just checked it a second ago, right? We looked at the discriminant, and we said that if you did that square root b squared minus 4ac, that would give you imaginary numbers. So we know that that's not ever going to have problems. So this thing is always good. No issues. We don't have any. So we only have one critical. Oh, I forgot to check. Is this in the interval? Oops. It is. It's in here, right? It's in there. So we have one critical number. We have two endpoints. We got to check them. All right? So let's do that. Step 2. I take the original function. I plug in negative 1/2. And then step 3, I'm going to take the original function, plug in negative 1, and then take the original function, plug in 1. And probably need my calculator for this. Not for that one. So unfortunately, you have to square the negative 1/2. It becomes positive 1/4, negative 1/2 here, plus 1. I can do the second one without a calculator because that's just natural log of 1, which is 0. This one is natural log of 3. And this one is natural log of 3/4, I believe. Is that right? Yeah, minus 1/4. Yeah, that should be right.
Okay, that's.
Did everybody follow? So what's my max? What's my min? Or you got to be careful with this. You got to make sure that this is not a negative number. Could be. Because remember, the natural log looks like this when you graph it. Right? It goes like that. And where does it hit here? At 1. So, natural log of 3/4 is going to be negative. Oh, this one will be positive. Yes, that's positive. So this should be my max, right? And this one should be my min. All right, any questions there? Look, I don't have enough time to keep working through examples, but that's what the homework is for. And I've also provided the video solutions. There's problems in there that involve e to the x. There's problems in there that involve sine and cosine. So you're just going to have to go and get your hands dirty, all right? The beginning of the homework for this section, they keep in the beginning problems, they keep it pretty nice, like nice little polynomial functions. And then they start getting a little more complicated, all right? So I would like for you to focus most of your attention for this section 4.1 on problems 23 through 49. Odd. I would start with odds. If you get through the odds, try the evens. You do that homework assignment as opposed to the one that's on the calendar. All right, just do that. I will mention that on problems 23 through 35, all it says is find the critical numbers. That's it. Then from 37 on, they give you a function in an interval and you have to go through the whole closed interval method, all right? So the first set of problems in here is just you taking the derivative, setting it equal to 0, figuring out where it doesn't exist, and then you're done. The second part of the problems, you have to go through this whole thing. All right. 4.1 is in the books. Now, you would probably assume at this point that I'm ready to talk about the open interval method, right? We're going to actually take a quick detour, all right? We are going to exit the highway for a moment, go to a rest stop here. It's not going to feel like rest, though. And we are going to cover a different idea. And I don't know, the book just does it in this order, so I'm going to go in the order of the book. We're now going to talk about what's called the mean value theorem. 4.2. The mean value theorem. Now, this is a very short section, all right? We're going to knock this out pretty quick. So the mean value theorem, when we say mean here, we're talking about average. Another word for an average is mean. And when I say average, I'm talking about like if you take like 4 tests and you want to find the average, right? You add them up, divide by 4. That's the average I'm talking about here. So this is the theorem that has to do with the average value of a function. The average value of a function, which is kind of a weird idea. So the first thing I'm going to do is I'm going to show you something called Rolle's theorem. Rolle's theorem is really, really nice because geometrically it's very easy to follow for most students. So here's Rolle's theorem. Rolle's theorem says, hey, let f be a function where these 3 conditions are met. All right? All right, so let's start with the first condition. F is continuous. You can draw it without picking up your pencil on a closed interval. Okay? Remember, we've taken a detour. I'm not talking about maxes and mins right now. Just talking about a function that's continuous on a closed interval. All right? So I'm going to start drawing over here. I have a closed interval, right? A to B. And it's a function that is continuous. So when I draw it from here to here, I can't pick up my pencil, right? Also, it says that it's differentiable on the interior of A and B. That means as long as you're not at the endpoints, everywhere except the endpoints, you need to be differentiable. Right? Those 2 conditions have to be in place. And then this third condition is a very strong condition. Look what it says. F of A equals F of B. That means that the y value at A is equal to the y value at B. So that means when I draw this, I have some freedom, but these 2 values at the end have to be the same. And now I have to connect those without picking up my pencil. All right, look at that picture right there. Do you agree that that picture satisfies every single one of these conditions? Is that a continuous function on that closed interval? Yes? Is it differentiable everywhere? How do you know that? Continuity implies differentiability or the other way around? You have to be careful with that. Can you be continuous and not be differentiable? Yes, you can be continuous and not differentiable. So you have to be a little bit careful. Can you think of a situation where I could draw it without picking it up but not be differentiable somewhere? A what? At a cusp. Couldn't I draw a cusp in there? Right? If I drew a cusp, like say I did this instead. Instead of that, say I did this. Would that be continuous? That's continuous. I can draw it without picking up my pencil, right? But is it differentiable everywhere? No, I have a place where it's not differentiable because I have a cusp, right? So the theorem says you must have continuity and differentiability, which we... That the derivative exists at every point in there. And by exists, we mean there's not a corner or a cusp or a jump or a vertical tangent. But if you had a jump, you wouldn't be continuous. So assuming that it has to be continuous, we just got to make sure there's no cusps, corners, or vertical tangents. This would be a vertical tangent, which would cause a problem with this theorem. It's going to be hard to draw. Something like, see how the tangent line goes vertical here? That would be a problem. This would not apply. This theorem would not apply. Yeah, that goes back to when we were talking about differentiability. Like where do functions fail to be differentiable? Corners, cusp, jumps, blah, blah, blah. Okay, so what is the conclusion of this? What is the conclusion? I've only said, here are the conditions. Continuous, closed interval. Differentiable everywhere inside. Okay, the 2 endpoints are equal. What does the theorem say we can conclude? Then there exists some number c somewhere in here. okay? So it's saying that somewhere in between here and here, guaranteed there's some value c in here such that what is true? That the derivative at that point, right, is what? 0, right? The derivative of that point at that point is 0. Do y'all see where it is? It looks like it's about right here. Let me move this c over. Do y'all agree that there does exist a c? There does exist a c somewhere in here that if I go up to that point on the graph, the derivative, the slope of the tangent line is 0. Yeah?
So we're ready to so can we have multiple C's?
It could be multiple. This says there exists a number, could be more than one. All right? Does that make sense to y'all? If I have to go from this point to this point without picking up my pencil and not having corners or cusps, then do y'all agree that somewhere my tangent line is going to have to be flat?
Yes.
Right? Do y'all notice that that flat tangent line is parallel to the line connecting these 2 points? Right? Coincidentally, right, the slope of that tangent line is parallel to the slope of this. What do we call a line connecting 2 distinct points? This is the tangent line, right? This would be a secant line, right? So this is saying that if there's a lot of conditions, these points have to be the same height and continuity and differentiability, that somewhere in here you're going to have a slope of 0, and that slope should be parallel to the slope of the secant line connecting those 2 points. Right? That's Rolle's theorem. Does anyone have an argument against Rolle's theorem that you can think of? Can anyone think of a situation where they could draw something that's continuous, it's differentiable, the 2 endpoints are the same, and this wouldn't happen?
Wouldn't it be the spiky one?
Which,
The spiky one that's like oscillation and it's spiky.
yes, so that would fail to be differentiable though, right? And we have to have the differentiability. So yeah, if you want to do that, then Rolle's theorem won't apply. So it's a theorem, right? Which means that there's nothing you're ever going to think of, right? There's no way, as long as you've got continuity and differentiability and the 2 endpoints are the same, then let me say it one more time. There's some point in here where the slope of the tangent line is parallel to the slope of the secant line. Yes?
Yes.
Okay, now let's move on. I was going to give you, I'm going to give you a couple examples. So there's an example. There's an example of Rolle's theorem, right? See that? They're parallel. Let me give you another example. See that? Is this continuous? Differentiable?
Yes.
2 endpoints are the same? Okay, so there's got to be at least one point where the slope of the tangent lines are parallel to the slope of the secant line. Well, actually it happens in 2 different places, right? The theorem just guarantees at least one, right? Okay. Third example. Is that continuous?
Yes.
Differentiable? Okay. What's the slope of the tangent line at every point? 0. What's the slope of the secant line?
0.
Yeah, so isn't it at every point in there?
Yes.
Doesn't matter what point you're at. The Rolle's theorem is satisfied. All right. Like I said, most people have no problems with the idea of Rolle's theorem. Makes sense. Now we get on to the theorem for this section, which is called the mean value theorem, which is just an extension of Rolle's theorem. I'll get to the theorem in a second, but just look at this right here. This is Rolle's, right? Rolle's theorem. There we go, like that. Imagine that we had this scenario where the 2 endpoints weren't the same anymore, right? Like this, right? Then could you say that somewhere in here the slope of the tangent line is 0? 0.
Yes.
Probably, but more importantly, is there a slope of a tangent line that's parallel to the slope of the secant line?
Yes.
Should still be the same thing, right? It's just kind of Rolle's theorem twisted, right? It's Rolle's theorem but kind of twisted. So what Rolle's theorem says is that as long as this red function is continuous and differentiable, and you throw away that third condition that these two have to be the same height, then what you can say is this, that somewhere in here there's a C such that what's true? The slope of the tangent line at C isn't 0, but it's equal to the slope of the secant line connecting these 2 points. And the slope of that line is rise over run, which is this, f of b minus f of a over b minus a. It's the difference of the y coordinates over the difference of the x coordinates. And so you get this instead of a 0 here. That's the mean value theorem. I'll put it up in my notes. See, in Rolle's theorem, right? In Rolle's theorem, what's the slope of this secant line? Rise over run, right? Rise over run. To get from this point to this point, what's your rise? 0. What's your run? Who cares? 0 divided by run is going to be 0, right? So it's kind of like, who cares? But if I twist this and it becomes the mean value theorem, then what we're saying is that now you actually have to calculate this slope. And so this side's no longer 0. It's the f of b minus f of a over b minus a. I hope that makes sense. All right.
It's just finding a new tangent.
We're going to do an example right now. It's weird to see how you use Rolle's theorem right now. Like when you first see a problem with this, because you're like, what are you actually going to do with this? All right. So here's the way these problems are presented. Say something like this. Verify the mean value theorem for f of x equals x over x squared plus 1 on the interval 0, 5. I think I'd like to start by graphing this for you, just so you can kind of see what we're working with here. I want a new one. New. So x over x squared plus 1. And I want this on 0, 5. All right, you'll see that over there? So we're supposed to verify the mean value theorem. I don't know why I made that so thick. All right, so what we're supposed to do is this. We're supposed to show that when you start this function at 0 and end at 5, right, that there's some line connecting these 2 points. That's called the secant line. Somewhere in here between 0 and 5, somewhere there's some value of x, which we are going to call c, that when I go to that point and go up and look at the slope of the tangent line, it needs to be parallel to this, all right? And you'll see where it is, kind of about, like, I don't know, maybe somewhere around here. It's not that highest point, is it?
No.
Because that highest point, the slope is what?
0.
0. We need it to be maybe a little bit over here, right? Yeah. Okay. Understand the geometry of what's going on? Okay, so let's verify it. First of all, what are the conditions? We need that to be a continuous function. Is it? Yeah, because the only thing that you could ever have as a problem is if the bottom is 0. And if the bottom can't be 0 here. Right?
Yes.
So this is continuous on that interval. Is it differentiable on that interval? Well, the only way to know that is to take the derivative and take a look at it. And make sure that we don't have any problems with the derivative on that interval. So first condition, f is continuous on 0, 5. Check. Check, that's a visual inspection. 2, f is, I'm going to put diff on 0, 5. Don't know, right? Don't know. So the only way to know that is to actually take its derivative. And the derivative of that's going to require the quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared, which equals x squared plus 1 minus 2x squared over x squared plus 1, that quantity squared. Sorry, I'm on the grid there. I think this is going to mess it up if I do that. Yeah, it's going to mess it up. All right, so what is that? Should just be 1 minus x squared on top? And on the bottom, 1, I'm sorry, not 1, x squared plus 1, that's squared. There's my derivative, right? There's my derivative. So is my function differentiable on this interval?
Yes.
Yes, how do you know? Not that we took it. When we look at this, we got to make sure we can plug every number between 0 and 5 into this without a problem. So again, the only issue I'd have to worry about is division by 0 here, right? And the only way that's happening is if this is 0, that's never happening. So is this differentiable?
Yes.
Yes. Okay. Questions there? That's it. For the mean value theorem, those are the only conditions you need. That's it. Now, let's verify the mean value theorem. Let's verify it. We have the two conditions met. So what does the mean value theorem tell us? I'm going to have to get rid of that graph. Sorry. The mean value theorem says the mean value theorem, I will abbreviate that MVT from now, says there exists a C in the interval 0, 5. It's actually not, it can't be one of the endpoints. The mean value theorem says that somewhere in between 0 and 5, right, some point between 0 and 5. So the mean value theorem says there exists a C in that interval such that this is true. The slope of the tangent line at C, right, the slope of the tangent line at that point should be parallel, so it should be equal to the slope of the secant line, which is f of b minus f of a, f of b minus f of a, all over b minus a. Do you all understand? You can write a note if you need to. This is the slope of the tangent line. This is the slope of the secant line. They must be parallel. Somewhere, there's some C that does that, right? We need to find that C. We are trying to verify this theorem is true, so we need to actually go find that C right now. Now, what is A and what's B for us?
0, 5?
Yeah, 0 and 5. So this is 0, that's A, and this is 5, that's B. And so I need to come over here and now say, figure out what these are. What is the derivative at C? What's the derivative at C? Well, there's my derivative, right? 1 minus x squared over, I'm sorry, not 1 minus x squared, 1 minus what? If I'm plugging C into it. 1 minus c squared over x, I did x again, c squared plus 1 squared, right? That's the left side. That must be equal to f of 5 minus f of 0 over 5 minus 0. So I'm saying somewhere at some value of c, the derivative, right, at that value of c must be equal or parallel to, the slope of the tangent line must be parallel to the slope of the secant line. So I've got to figure out what f of 5 is and f of 0. What's f of 5? So I'm continuing left side and right side down. 1 minus c squared, this marker sucks, over c squared plus 1, that quantity squared, must equal, what's f of 5? 5 over 26. And then minus, what's f of 0? 0, so I don't need that there. And then all over 5, right? All over 5. Plugging, so I'm just figuring out what f of 5 is, right? So 5 over 25, this is 5 squared, and then plus 1, 26.
I plugged it into the.
Oh, you plug it into the, okay, got you. No, we were doing the original function here.
So we plug in 5 and 0 back to the.
To the original function, yes.
And then we would do 526.
What does that become?
We multiply that by.
Flip,
Flip.
5s cancel.
Yeah.
So you'll get just 1 over 26? That okay? Do what? Yeah, there's so many different ways. Did you say butterfly?
Yes.
It's probably some method you heard. Maybe like cross multiply. I don't know. People are going to have learned different things here. We have to solve for C here, right? Do y'all see it? We have an equation for C we have to solve. And I made up this problem on the fly here, so I'm pretty sure we're going to have a problem solving this. But let's just see. Let's just keep doing the algebra. So I'm going to multiply. I'm going to cross multiply like this. 26 here, distribute it through, and then this times 1. So I'm trying to solve for C. And I think I'm going to run into a problem. Trust me, on your homework problems, it'll be easier equations to solve. Maybe a quadratic will be about as bad as it gets. All right, so I'm going to have 26 times 1 minus c squared, and then equals, this right side is c squared plus 1, but all that squared, right? Distribute through 26 minus 26c squared equals, okay, there we have to square that, don't we? Which means you have to like FOIL it out. Don't just square each one, right? You have to do that times itself. If you do that, you'll get c to the 4th plus 2c squared plus 1. Not showing that work. And we might be able to do this. Let me move everything over to one side. Subtract 26, add 26c squared. Add 26c squared, subtract 26. We get 0 over here, c to the 4th, plus 28c squared minus 25. Damn, that doesn't work. You all see what I've done? Now, we could actually solve this. This is, from college algebra, this is called a quadratic type. Quadratic type. Because it's instead of squared here in first power here, we have 4th in second power. So it could still be solved using a substitution, or you could do like a U substitution. I'm not going to take it the rest of the way, because I would never give you something like that on a test, because it would take too much time. The worst that this would be in a real problem was this would be quadratic. And then you could always use quadratic formula. So is it all right if I just have the computer solve it for us? Okay. So I'm going to solve. And part of why I want to go solve this is because I want you to see the computer gives us an answer, right? And I want to kind of, later on, I want to talk about, not this class, how the computer solved this. Where is it? Plus 28c squared. And then minus 25? Minus 25 equals 0. We should get at most 4 answers, at most. And let's get decimals.
Oh, because of the plus and minus.
Yeah, there are 2 imaginary roots to this. So it's looking like the only ones that really matter to us are the plus, plus, because what our interval is between 0 and 5, right? So plus 0.93, right? Plus 0.931, something like that. Okay? Let's check. I'm going to go back to the graph that I had here. I'll make that less thick. That was a little overkill there. Okay, now I'm going to do something here. See what happens if I put f of x. I think it'll still work. Yeah, there we go. So now y minus f of m equals so I just made a quick little thing that I can slide around here to give me the tangent line. And then this is m comma f of m. And there's the point. Let's make it blue. So I can just take this point and drag it around here, see that? And get my slope. And 1/26. So let me go. There we go. So that's the part of the secant line. Do I need to erase some of that? I'm sorry. Forgot I had all that stuff there. All right, so the question is, what x value do I go to make this black line and this blue line be parallel? And we said, what, 0.93? So I'm going to move this value of m right here to 0.93, and it should be parallel. And to make this really kind of nice, I'm going to go 0.9 there and 0.98. That way I can really refine it. You see it going there? If I go 0.9, what was it, 0.931? Right around there. Look pretty parallel to you? Yeah, me too. So the mean value theorem says that as long as you've got continuity and you've got differentiability, then this will always happen. Why do they call it the mean value theorem? Right? It's mean, it's a mean problem. No, because if I were to go back to this idea from college algebra, let's do something easier to understand. Like if this is time, and let's say that this is distance. Right? Then let's say at 1 hour, we've gone 30 miles. So this is going to be miles. This is going to be hours. So we're on some trip. At hour 1, we've traveled 30 miles, okay? And what if I tell you that at hour